So let's do some approximations. All right, sometimes you might be able to get rid of some of the plus or minus x's that um, appear in your ice table. And this happens if the initial concentration of some of the species is much larger than the value of k itself. I personally like to look at it from this point of view. If you take the ratio of the initial concentration of one of your species and you divide that by the value of k, if this ratio ends up being greater or equal than 400, then whatever x plus or minus x that you have in your equilibrium expression from the ice table, that x can actually be disregarded, right? So the change in concentration will tell you in this case is going to be pretty negligible. If the value is less than 400, then the change in concentration is not going to be very close to zero. It's actually going to be a non-zero value. So the idea is that if you take the ratio of the initial concentration over the equilibrium constant, and you get a value that is equal or greater than 400, the plus x's and minus x's for that particular species can be disregarded from your equilibrium expression. On the other hand, if the value is less than 400 when you take the ratio, you must keep the plus and minus x's present in your expression for that particular reactant or product. Alright, so just to give you a proper example, looking at the same reaction once more, but I'm changing the concentrations ever so slightly. Now I have 2 molar as my initial concentration for N2O4. The equilibrium constant, of course, is the same as we had for the previous video because it's the same reaction at the same temperature. So for the initial concentrations, we have 2 for N2O4 and 0 for NO2. The change in concentration will be minus x for N2O4 and plus 2x for NO2. And when you add these two rows together, you'll find out the equilibrium concentration to be 2 minus x and 2x for N2O4 and NO2 respectively. Alright, so if we write the expression, the equilibrium expression, the expression will be 2x raised to the power of 2, all divided by 2 minus x. Alright, now for the expression that has the plus or minus x's present, so here we're subtracting x from 2, we take a look at that concentration of 2. Specifically, we divide that concentration by the value of k. So we have 2 divided by 4.61 times 10 to the negative 3. And if you do that in your calculator, you're going to find out the value to be greater, not by a lot, but it's still greater than 400. So what this is telling you is that the change in concentration for N2O4 is going to be pretty small. Small enough that we could say that the 2 minus x is actually pretty much the same as saying just 2. So we're saying the x is negligible. We take it out of the equation altogether. And so this kind of simplifies the process a lot because all we have to do now is multiply both sides by 2, which is going to equal 4x squared. Right, so here if you multiply 4.61 times 10 to the negative 3 by 2, you're going to get the following value, 9.22 times 10 to the negative 3. That equals 4x squared. But you're going to have to solve for x anyway, so instead of just squaring the 2x, you could simply take the square root of both sides. So if you take the square root of 9.22 times 10 to the negative 3, you get a value of 9.60 times 10 to the negative 2, which equals 2x. Divide both sides by 2, and voila, you found the value of x. And this only took me 3 steps to get to the value of x, which is to be contrasted with what we did for the quadratic formula, which took easily like 6 or 7 steps just to get to the final thing. So this approximation works out really great, but it relies on the idea that the concentration of your species divided by k gives you value greater than 400. If it does not, you cannot remove the minus or plus x that you have. Now one question that you might ask is like, well, what about NO2? Why don't you divide the initial concentration of NO2 by the equilibrium constant? And you could do that if you wanted to, right? You could say 0 divided by k, that's just going to be 0. But irrespective of that, the x that you have here is not being added to a value that is not 0. The x is being multiplied by 2, and that's all you're doing. So this x you cannot disregard, even if the value here will be quote-unquote greater than 400. Because if you do that, you're going to end up with 0 for the equilibrium concentration of NO2, and then you end up with a situation that is just technically fully incorrect. So the removal of x's in the approximation are only for x's that are being subtracted or x's that are being added to a non-zero number. All right, now, since we found the value of x, you must remember that that is not what you're trying to find out ultimately. What you need to get is the equilibrium concentrations. And since we use an approximation to find out the concentration of, or excuse me, the value of x, we need to make sure that the approximation still holds true. So if you input the value of x into the table, so subtract 4.8 times 10 to the negative 2 from 2, and multiply that value by 2 for the concentration of NO2, you're going to find out that the value of N2O4 is 1.952, which if you keep it to the 3 sig fix, which is what you started with, this rounds up back to 2, right? So at least close enough, right? So that's telling you that yes, your approximation, of course, introduces some error, but it is relatively okay, which is why we use this. And notice that because the ratio that we had before was close to 400, right, we have a little bit of error, right? 1.95, if you bring it down to 3 sig fix, is not exactly equal to 2, but it's close enough, right? And the larger the number gets for the ratio, the more accurate your approximation is going to be. Here we're kind of like getting borderline in terms of the accuracy. Alright, so that's one thing that you can do to simplify your um, process of solving for the equilibrium concentrations. But there's a few other instances that can help you out that are even more precise than the approximation. And this has to do with exponents. So let me switch to a different reaction. We have H2 plus I2 reacting to give you 2 HIs. And I'm keeping the initial concentration of H2 and I2 the same, 1 times 10 to the negative 3. The equilibrium constant is equal to 51. We found that out in an earlier video. Question being, what are the equilibrium concentrations? So once more, you have to set up an ice table. You have H2, I2, and HI. The initial concentrations are given for H2 and I2. Nothing is being said for the initial concentration of HI, which means that we assume it to be 0. Now the change in concentrations, once again based on the coefficients, minus for the reactants and plus for the products, will be minus x for H2, minus x for I2, but it'll have to be plus 2x for HI. So those are the changes in concentration. Add the two rows together and you have now your equilibrium concentrations. Alright, if we now input the equilibrium concentrations in terms of x into the equilibrium expression, we have to have the 2x raised to the second power and the 1 times 10 to the negative 3 minus x raised to the first power for both H2 and HI, right? So you have the following expression, which equals 51. And because the concentrations, and more importantly, the expressions for the equilibrium concentration are the same for H2 and I2, technically speaking, you have 1 times 10 to the negative 3 minus x times 1 times 10 to the negative 3 minus x, which is the same thing as saying 1 times 10 to the negative 3 minus x squared. And notice what we have right here. This is actually a very unique situation. We have an exponent for the product, which is the same as the exponent for the reactants. And so what we can do is literally factor out the exponent. So instead of writing 2x squared divided by 1 times 10 to the negative 3 minus x squared, we simply write 2x divided by 1 times 10 to the negative 3 minus x, all of that squared. So you can actually factor out common exponents. And this simplifies the process a lot because all you have to do now is take the square root of both sides. And if you do that, you're going to get rid of the nasty expression you have here on the right side. You're going to end up with a new number. The square root of 51 is 7.14. The square root of the expression here on the right is simply the ratio 2x divided by 1 times 10 to the negative 3 minus x. And what needs to happen now is that you multiply both sides by 10 to the negative 3 minus x to yield the following expression. 7.14 times 10 to the negative 3 minus 7.14 times x equals 2x. Add 7.14x to both sides, you will have 7.14 times 10 to the negative 3 equals 9.14x, which tells you that you have to divide both sides by 9.14 to find the value of x. So once again, we simplify the process. It took maybe 4 steps or so to get to the value of x, but it is still an easier version of doing the quadratic formula. By the way, you could still get to the value of x by using the quadratic formula, so that's still a possibility. It's just going to take you extra steps to carry out the calculation. But now that we have the value of x, we just need to input that into the expressions, right? to find out the value of x. And yes, if you multiply by 2, you're going to get 1.56 times 10 to negative 3. Subtract the value of x from 1 times 10 to negative 3. You're going to get the following values for the equilibrium concentrations of H2 and I2. So this is another means by which you can find the equilibrium concentrations. It relies, of course, on the fact that the exponents for the products and the reactants are the same. If they are not, then you really can't do what I did to solve this problem. All right, one last thing to be considered. This is the QC approximation. And this is actually something you have to do if you actually have initial concentrations for everything. Because before, what we saw is that one of the components, at the very least in the equilibrium expression, was equal to 0 as an initial concentration. So we knew that we had to move to that particular end of the reaction. But when you have initial concentrations for everything, as is the case in this example, it's not exactly obvious whether this is going to be moving to the product side or if it's going to be moving to the reactant side. Because remember, this can go forward or it can go backwards. So you have to actually do a calculation first before you come up with the changes in concentration for the ice table. All right, and so what you do is you simply come up with the equilibrium expression, which is Hi squared divided by H2 divided by I2. But because you don't know the equilibrium concentrations, this is not the Kc expression, it's actually the Qc expression. And the expression for Qc is always going to be based on the initial concentrations of reactants and products that you have. So we're going to input the values. All of them are 1 times 10 to negative 3. So we input those values into the expression. And what you end up finding out is that you end up with value square on top and the value square on the bottom. So they cancel out, meaning that the value of Qc is actually equal to 1. All right, now, in and of itself, the value of Qc doesn't really tell you anything. What you have to do is compare it to the value of Kc. And the comparison goes as follows. If you set it up alphabetically, so K before Q, all you have to do is compare the numbers and see whether K is greater than Q, less than Q, or equal to Q. If K is greater than Q, much as the way the arrow points, the reaction is going to be moving to the product side, right? So wherever this arrow points, as long as you set up this alphabetically, K before Q, this will tell you which direction the reaction is going to go. If K is equal to Q, there's no change. You're already at equilibrium. But if K is less than Q, this will tell you that you're going to move to the reactant side. And for a specific example, K, which is 51, is indeed greater than the value of Q. So in this particular case, the reaction is going to be moving to the product side. So now that you know that, you can finally go back to the equilibrium expression and say that, okay, we're moving to the product side. So you're going to decrease the reactants and you're going to increase the amount of product. So this is minus x, and plus 2x, which looks very similar to what we did in the previous examples. But be mindful of the fact that for this specific example, it did work out that way. But if the value of Q would have been larger than the value of K, then the minus x's here would actually have been plus x's, and the plus 2x would have been minus 2x. So that's how that would have changed the entire picture. Oh, okay, so now getting to the equilibrium concentrations, we added two rows together. And looking at the expressions, we have 10 to the negative 3 plus 2x squared divided by 10 to the negative 3 minus x, also squared. Because you have squares on both sides, you could actually use the approximation I showed in the previous example. Factor out the square. Take the square root of both sides to get the following expression. And if you cross multiply both sides by 10 to the negative 3 minus x, you're going to end up with the following expression. Here you have to move the x terms to the same side, move the non-x terms to the opposite side, so that you end up with the following expression. And then you divide by whatever the coefficient in front of the x is to solve for x. Once you have the value of x, once again, don't forget to multiply it, right, in this case by 2, and add it or subtract it from the other expressions. So you end up now finding out the true equilibrium concentrations of your reaction. So this one was a little bit more convoluted, but as you can see, the procedure is still the same. You come up with your changes in concentration, you set up your equilibrium concentrations in terms of x's, set up your equilibrium expression, and then you solve for x. All right. that concludes the mathematical portion of the equilibrium chapter. In the next video, we're going to look at the qualitative portion, which is the Chatelier's principle. So see you in the next video.